Hello everyone, welcome to this video. In this video, we shall be looking at the proof of this result that we have studied in the previous video. So here we wanted to prove that orbits of different members of S that constitute a partition for S. So remember what is the definition of orbit of a point? The orbit of some point small s, which is a member of this capital S, right? So under the group G, it is defined by taking the image of this element S under all such phi's which are members of G, right? So we are taking the image of this point S under all the permutations which are given in the group G, right? This is the definition. Now here, because you know this set the orbit of S that is giving us the images of each of these element S. So what is the images? Images is again an element of this S, right? So obviously this orbit G of small s, where this small s is a member of capital S, this is a subset of the set S. Why? Because here the elements which are obtained in the orbit, they are the members of S only. So we can write S, the set S, as the union of all such x such that x is a member of S. So it is simply writing 1 union with 2, union with 3, union with 4, union with 5, union with 6, union with 7, union with 8 in the previous example. So this is writing the same thing, and now we can write each of the element as ex. We can write x as ex, so there is no issue. So we have written S as equal to the union of ex, where this x is taken from the set S. Right now, in order to show that orbits of the members of S, they constitute a partition of S, what we need to prove? We need to prove that whole of this set S is contained in this union, right? Union of orbits, and all the orbits, they are either equal to each other or they are disjoint to each other, right? So their intersection is empty. So this is what we wanted to prove here. So what we are saying, we are claiming that either this intersection is exactly empty. If it is not exactly empty, then they are exactly equal to each other. So they are either equivalent to each other or they are disjoint to each other for all AB which are member of S. So in order to prove this thing, in the first case, if this intersection is empty, then we are done there. Then there is no need to prove anything, because this is what we required. So let us assume that this is non-empty, right? So we assume that this is non-empty. If this is non-empty, so that means there would at least be one element which is present here. So let's call that element as C. So this element C is present in this intersection. So that means the element C is present in both of the sets, right? So it is present in the orbit of A and it is also present in the orbit of B. So now what is the definition of orbit? According to the definition of orbit, we would have the set of orbit as consisting of all the images of the C under the group G. So we consider phi 1 and phi 2 be two permutations from G such that phi 1 of A would give us C and phi 2 of B would give us C, right? So all the images of A, they are equal to C, because C is some member here, so therefore it would be the image of some permutation, and C is a member here in the orbit of P, so therefore it would be the image of some permutation, say phi 2, right? It could be anything, so we are assuming them to be phi 1 and phi 2. Now because this phi 1 and phi 2, they are permutations in the group G, and G is a group, so therefore this permutation phi 1 inverse phi 2 would also be there in G, and phi 2 inverse phi 1 would also be there in G, because G is a group and group has the closure property, right? So it would also has the inverse of that permutation, and we have the closure property also present here. So now let's consider this element A. So from here, because phi 1A was equal to C, so what is the value of A? A is equal to phi 1 inverse of C, right? Similarly, what is the value of B from here? B is equal to phi 2 inverse of C. So we have A as phi 1 inverse of C and B as phi 2 inverse of C. Now if you see, what is the value of C here in terms of B? C is equal to phi 2B. So we have written down just that value, and using the associativity here, it is equal to phi 1 inverse phi 2 of B and phi 2 inverse of C. Here we are using the definition for this A, right? So see, this C could be written as phi 1 of A, right? So using the associativity property, we have phi 2 inverse phi 1 is equal to here we have phi 2 inverse phi 1 applied onto A. So let's mark this as equation number star. Now because we wanted to prove the equality here, right, the equality of these two orbits, what we do is, in order to prove this equality, we prove that for one is a subset of other and other is a subset of first. So in order to prove this thing, we firstly prove that orbit of A is contained in orbit of B. In order to prove that, we consider some element x from here and we prove that this x is also present here. So we assume that this x is a member of orbit of A. If that is so, according to the definition, there would be some permutation in G, let's call that as phi 3, such that when we apply phi 3 onto this A, we would have x. This is according to the definition of orbit. So we have x is equal to phi 3 of A. So that means x is equal to phi 3 of A, and according to the equation star, what is the value of A? If you see, the value of A is equal to this phi 1 inverse phi 2 of B. So we have the value of A as phi 1 inverse phi 2 of B. Now we can use the associativity and we can rearrange the brackets so that we have phi 3 phi 1 inverse phi 2 of B. Now this is another permutation, right? This is present in G. So therefore we have this element x written as some permutation times B. So that means this x is a member of orbit of B, because this x is now image of the element B where this is some permutation in G, right? So therefore it is present in the orbit of B. So we started by taking this x from orbit of A and now it is present in orbit of B. So therefore orbit of A is contained in orbit of B. So this proves the fun part here. Now in order to prove the reverse, we need to prove that orbit of B is present in orbit of A. This is a subset of this orbit of A. So again what we do, we consider some element here and we prove that this element x is also present here in the orbit of A. So let's consider x in the orbit of B. So that means if it is present in orbit of B, so that means x is the image of this element B. So let's apply, let's say the permutation there would be phi 4. So that means when we apply phi 4 onto B, we would have x as the image. So this is according to this definition. So we have x is equal to phi 4 of B. Now if we have x is equal to phi 4 of B, now according to the equation star, what is the value of B? So you see the value of B, that is equal to phi 2 inverse phi 1 of A. So using this thing here, we have phi 4 as such, phi 2 inverse phi 1 of A. Now applying the associativity and rearranging the brackets, we have phi 4, phi 2 inverse phi 1. Now because phi 1, phi 2 and phi 4 all are permutations which are taken from the group G. So therefore this composition is also present in G. So that means we can write our x as some permutation in G times A. So that means this x becomes the image of this A under the permutation which has been taken from G. So right, this x is now a member of orbit of A according to the definition of orbit. So we started by taking this x from this orbit of B and we have now obtained that x is some member of orbit of A in G. So therefore orbit of B is a subset of orbit of A and hence we have this equality. If we have this equality, so our claim is true. We have claimed that their intersection is either empty or it is equivalent. So therefore because S is contained in this union of orbits, so therefore this orbits of the members of X, they partition S, and this is what we wanted to prove here in this theorem. So I hope you understood this proof and this result well. Well, that is it for this video. Thank you for watching.